Greetings everyone from the other side of the world. Before I begin, I would like to thank the organizers of this conference for understanding our unusual circumstance and allowing us to present remotely. I'm Chris, and I'll be presenting Depth Adaptive Computational Policies for Visual Tracking. First, some quick notes about us. I'm currently working at Google Brain in California, but this work was done while I was a master's student at Carnegie Mellon University's Machine Learning Department. My advisor and co-author is Katerina, who is a professor and researcher at CMU. I will have our contact information at the end of the presentation in case you would like to reach out to us about our research. Let's begin with some observations. In the last 5 years, we've seen an incredible explosion in advances in computer vision, largely driven by deep neural networks. On this slide, I have listed 3 very influential convolutional architectures in computer vision: AlexNet, VGGNet, and ResNet. A trend you can see is that these models are getting deeper and deeper. A consequence of these models becoming deeper is that they also require expensive computation. For example, AlexNet and VGGNet each take over 1 billion floating point operations for a forward pass through a single image. And this is just for evaluation. Training is even more expensive. In order to run these models in a reasonable amount of time, we often use GPUs and other specialized hardware, which are expensive and often not fast enough for tasks that require real-time results. This problem is particularly relevant nowadays because deep learning is starting to arrive in mobile devices, which do not have enough power to run expensive neural networks. There is a lot of other research in learning less expensive but similarly powerful networks to solve tasks. This work takes a bit of a unique approach to this problem. We first make the observation that convolutional neural networks are just fancy feature extractors. In general, the deeper you get in a network, the more high-level information you learn about the image. For example, in AlexNet, the early convolutional filters learn things like edges and patterns and textures, and as you get deeper in the model, it starts to learn more complex features like eyes and wheels, as you can see from the intermediate features in this picture. This leads us to the key idea in our research, which is, what if we could learn a policy that uses conditional computation to dynamically determine the depth of the network to evaluate? I highlighted a couple words in this sentence. We want a policy that determines how deep we should evaluate a network because we want to take advantage of the fact that some examples in a task might be easier to solve than others and may only need shallow features. Conditional computation is highlighted because we want to determine how deep to run per image so that we can conditionally halt computation in order to actually save time. The task that we apply this idea to is visual tracking. There are many forms of visual tracking, and the task we tackle specifically is one-shot learning. The input is a labeled frame of a video, hereafter referred to as the keyframe. The label is a bounding box for a single object in the video. The following frames of the video are unlabeled, and the task is to output the bounding box for each successive frame, now referred to as the search frames. The dataset we use is the Video Object Tracking 2016 dataset, which is from an annual tracking competition. The dataset is selected because it has a wide range of video tracking tasks with a wide range of difficulties. In some videos, the object may change appearance or even become occluded. You can imagine that we should be able to take advantage of a depth adaptive policy in order to save computation on many of the easier frames without losing tracking quality on some of the more difficult ones. The baseline model we use is a fully convolutional Siamese network. Fully convolutional refers to the lack of fully connected layers in the architecture, which usually show up at the end of the model. This allows us to be fully scale invariant. The network can accept images of different resolutions without changing the learned parameters. And we can use pre-trained weights from the convolutional layers of some other model. A Siamese network is a type of network used for similarity learning. Generally, you feed in 2 examples to the same network, then use some similarity function to compute how similar the embeddings are. In this case, we feed the slice of a keyframe and a slice of the search frame into the same convolutional neural network, then use cross-correlation to find the most similar locations within the image, as you can see from this example on the slide. Cross-correlation is essentially just doing a convolution over the search image with the keyframe as the filter, multiplying the keyframe at every spatial location. The result is that the model we have allows us to perform deep spatial similarity with pre-trained weights, so that we do not have to spend as much time training our model. Now back to the original idea we had. We want to learn a policy to perform tracking at different network depths. This diagram is a slightly more detailed version of the baseline architecture from the previous slide. For the convolutional part of the network, we use a VGG19 architecture. We divide the network into 5 chunks of convolutions, each with 2 to 4 convolutions followed by activations and a max pool operation. Everything is implemented in TensorFlow and run on GPU. The first big modification we make is we add cross-correlation outputs at multiple depths in the network, in this case at the end of every single convolutional block. This doesn't actually do conditional computation yet, so the next step is we add gating functions between each convolutional block which control whether we stop or want to continue computing in the network. These gating functions look at the cross-correlation maps and predict a confidence score which represents how certain we are over the prediction from the current depth. Now let's take a deeper look at these gating functions. The gating confidence score is a simple linear function of some extracted features from the cross-correlation maps. We apply a sigmoid function to ensure that the scores are between 0 and 1. The extracted features can vary, but for our model, we selected some statistics which logically encode the quality of the maps, including the first few moments, the kurtosis, which measures the peakiness of the graph, the value of the highest few peaks, and some other hand-selected features. We use hand-selected features instead of learned features because we want our gates to be very fast to run, so having a convolutional neural network wouldn't work for this case. However, just this gating function is not enough. When training the network, we found that the gates were very hyperparameter sensitive and often polarized, which means that the gates would always give 0 or 1 prediction for the shallowest or deepest layer depending on the hyperparameters. The solution to this is something called budgeted confidence scores. Essentially, the idea is to introduce backwards dependence between the gate functions at each depth. Each gate gets a budget of how much confidence it can assign, which is dependent on the confidence scores of the shallower gates. A high confidence score early on in the network means that the deeper gates have less budget to work with. Since we have five cross-correlation maps, the 5th budgeted confidence score receives the remainder of the budget after the first 4 gates. Because the gate feature extractor is non-differentiable, training the network proceeds in 2 phases. First, we fine-tune the network weights, ignoring the gate parameters, by optimizing a loss function which incorporates the tracking accuracy at each depth. It is absolutely crucial to use the loss at every depth, otherwise the network tends to perform poorly until the very last layers. The next phase of training is the gating functions, where we fix the network weights, which are mostly convolutional weights, then train each gating parameter with a loss function which combines the weighted tracking loss weighted by the gated confidence scores, the budgeted confidence scores, and also a term that encodes the computational cost. The computational cost term encourages the network to perform cheaper computation. Lambda is a hyperparameter which controls how much we value the computational cost and can be tuned depending on your task and your needs. The actual policies which we use on our gates are the following. As baselines, we have fixed depth policies which unconditionally uses the cross-correlation maps at each of the 5 depths. This policy does not use the gating, the budgeted confidence scores at all. We also have a soft gating policy which outputs a prediction based on the weighted sum of each cross-correlation map with the budgeted confidence score. This doesn't actually save computation, but is a good comparison to see how good our confidence scores are. The hard gating policy is the conditional computational policy, which halts computation whenever the gated score is above some tunable threshold. This threshold can be varied depending on your task, and we compare results at many different thresholds. Now onto some results. Here are 4 selected tracking outputs with their keyframe, search frame, and all 5 cross-correlation outputs for demonstration. The white numbers are the budgeted confidence scores. As you can see in the first 2 examples, the tracker is fairly confident even at the first depth, since the object doesn't change very much in the search frame. In the last 2 examples, the object is much more difficult to distinguish, so the network is not as confident until the later depths. With the hard gating policy, we would halt computation at the first block for the easy example, but would proceed until a deeper block before we are confident enough to halt computation for the more difficult frames. The grayed out components of the network in this slide are not actually computed under the hard gating policy during evaluation. Now let's go on to some results. When fine-tuning our network, we found that using pre-trained weights from ImageNet were fairly good, so the test accuracy of the tracking plateaus after around 5 epochs. Though we were not aiming for state-of-the-art accuracy with our network, we were actually fairly competitive with many of the competition winners of VOT 2016, despite missing some key tracking-specific optimizations. We calculated the number of floating point operations needed to compute up to each step in the cross-correlation maps. The deepest layer takes about 10 times as much computation to execute than the shallowest layer. This is probably the most interesting plot from our work. We compared each of the policies which we mentioned earlier. In this plot, the top left is more desirable, with higher accuracy and lower computational cost. The blue dots are the fixed depth policies, which do not use the gates at all. As expected, using more layers tends to increase the accuracy, measured as intersection over union, averaged over 25 frames. The green triangle is the soft gating result, which uses the weighted sum of the cross-correlation layers. Interestingly, the soft gating policy actually does better than the baseline cross-correlation maps, even at the deepest layer, which means that the deepest layer is not always the best predictor. The most interesting part is that the hard gating seems to universally do better than the fixed depth policies at basically all network depths. We plot multiple results with different hyperparameter settings by varying the loss function and varying the threshold in which we stop computation. The results show that you can successfully trade off accuracy for speed and still beat fixed depth computational policies with our model. Here is an output tracking video of our algorithm being run on a video from the dataset. The green box is the ground truth bounding box, which we receive at the first frame of the video. Our tracking is a little jittery due to the resolution of the cross-correlation maps being fairly low after 4 max pooling operations. Unlike many other video tracking algorithms, we do not update the object model through tracking, so we are using the first frame as comparison for all frames. We could probably significantly improve our tracking metrics if we updated our model, as well as a few other optimizations, like bounding box resizing and temporal smoothing. But these methods are orthogonal to the research that we were doing. I'll let the video run to completion before going back to the presentation. This work really only scratches the surface for depth adaptive policies. For starters, our tracking is not state-of-the-art yet and has many opportunities for improvement. We did not explore this too much because our goal was to demonstrate a depth adaptive policy, and visual tracking just happened to be a good task for the experiments. One part of the network which was not wholly satisfying for us was that the gating functions could not be jointly trained with the network weights, since the feature extractor were hand-designed features. In the future, we may explore learning cheap and also effective features automatically for these gates, maybe with very small convolutional neural networks. Lastly, the most important takeaway is that we successfully demonstrated an elegant method for varying the computational cost of a network by dynamically adjusting the depth of the network. This can be extended to many other tasks in computer vision and other disciplines as well, which use convolutional neural networks or other deep learning architectures. Thank you all for your time, and we are really sad that we could not be here in person to hear about all of your projects. If you have further questions, please email us at the addresses below. Thank you so much for your time.